Hello, my name is Lucas Anderson, and we are MavForce from the University of Texas at Arlington. And our senior design project is a collaborative UAV/UGV autonomous system developed for the Raytheon Autonomous Vehicle Competition. Our project supports the 2025-2026 competition theme Operation Touchdown and focuses on autonomous navigation, target identification, and collaborative autonomy between an unmanned aerial vehicle and an unmanned ground vehicle.
In order to complete the competition, the UAV must autonomously launch from the UGV, search the field for the designated RUCO marker, communicate that destination directly to the UGV without using a ground station, and then land on the moving UGV while the UGV navigates to the target and avoids obstacles. This challenge is relevant to real-world applications such as disaster response and defense, where aerial systems can scout the terrain and improve effectiveness of ground systems.
Our system is organized into three main layers: the UAV, the UGV, and the ground station. The UAV acts as the aerial scout. It is built around the Cube Orange flight controller and the Raspberry Pi 5B companion computer, and it is responsible for takeoff, onboard vision processing, target acquisition, and landing back on the moving UGV. The UGV serves as the mobile base and destination vehicle. It also uses a Cube Orange and Raspberry Pi 5B, and is designed to transport the UAV while avoiding obstacles and provide a stable landing deck. The ground station is used for telemetry, mission logging, and emergency kill switch control.
Our technical approach focuses on four main challenges. First, the UAV must detect a 12-inch by 12-inch RUCO marker and estimate its location accurately enough to guide the rest of the mission. To do that, the UAV uses onboard vision and edge inferencing to process camera data in real time while it searches the field. Second, once the marker is found, the UAV must communicate the destination directly to the UGV without relying on the ground station, which is required by the competition. Third, the UGV must navigate in a GPS-denied environment while avoiding real three-dimensional obstacles such as cones, boxes, or tires. Finally, the UAV must land safely on the moving UGV, which requires coordinating relative position, motion, and timing between both vehicles while they are operating autonomously.
The UAV uses a layered hardware and software design to separate flight control from higher-level autonomy. Its main hardware includes a Cube Orange flight controller, a Raspberry Pi 5B companion computer, a setup of stereo vision cameras, a downward-facing camera for landing, and a BrainChip module for on-the-edge AI interface. On the software side, the Cube runs ArduPilot for stabilization, safety, and low-level control, where the Raspberry Pi runs Ubuntu and ROS2 for perception, mission logic, and coordination. OpenCV supports RUCO detection, and MavLink connects the companion computer to the flight controller.
The UGV is designed to act as both a ground vehicle and the UAV's mobile landing platform. Its main hardware includes the motor, the servo, the landing platform, the Cube Orange controller, the Raspberry Pi 5B, the LiDAR sensor, and wireless communications. The Cube handles low-level robot control and safety functions, while the Raspberry Pi runs Ubuntu and ROS2 for high-level autonomy. On the UGV, ROS2 is used to create a map of the environment using LiDAR scans, and maintain an estimate of the vehicle state using sensor fusion to plan a path to the target RUCO marker. This lets the UGV navigate in a GPS-denied scenario while controlling speed and heading to avoid obstacles, even during UAV landing sequences.
Our testing strategy is divided into subsystem testing, integration testing, and full mission testing. Subsystem tests evaluate individual capabilities such as autonomous takeoff and landing, RUCO detection, and UGV obstacle avoidance. Integration tests verify that the UAV and UGV can exchange mission information and transition correctly between mission phases. Finally, since UTA will be hosting the competition, full mission tests are performed on the competition turf field with an RUCO target and a stationary obstacle to evaluate autonomous operation.
Currently, we have demonstrated RUCO detection, autonomous UGV navigation, and manual flight of the UAV. In our latest testing, our computer vision model can detect cones, tires, and boxes up to an 83% accuracy. The main challenges we are continuing to improve are autonomous flight, GPS reliability, and IMU/LiDAR sensor fusion accuracy. These results are helping us tune the full system for reliable outdoor operation. Currently,
in summary, our project will demonstrate a collaborative autonomous platform in which a UAV and UGV work together to identify a target, share mission data, and navigate in a constrained environment to complete a coordinated mission. Beyond the competition itself, this work gives our team hands-on experience in autonomous vehicles, computer vision, and GPS-denied navigation. Our next steps are continued subsystem integration, outdoor testing, and improved reliability in detection and navigation.